Hello everybody. This video is about the diameter of a network. This commonly used metric often communicates how large a network is. To give us a sense for what exactly the diameter is measuring, let's think about playing a particular game. Suppose I give you a fixed network like the one before us, and I randomly choose a starting point and a stopping point. So for example, maybe my starting point is in red and my stopping point is in green out here. Now, since my starting and stopping point are randomly chosen, you won't know exactly how far you'll have to walk to get from point A to point B on any given iteration of this game. However, you could answer the question, worst case scenario, how far am I going to need to walk in order to play this game? This is what the diameter is going to try to measure. Now, before we move on to actually computing a diameter, we have to talk about the difference between walks versus paths. A walk is simply just a sequence of adjacent nodes. So you might represent a walk in the following way: A, D, A, B, D, A. This would mean you start at A, you go to D, you come back to A, you go up to B, walk over to D, and then back to A. Any sequence of adjacent nodes, meaning you can move from one node to another if and only if there's a nice edge in between them, any sequence of adjacent nodes is considered a walk. Now we'll be interested in this video in working with paths. A path is also a sequence of adjacent nodes, but we have to make sure that we don't use nodes or edges more than once. Here's an example of a nice path. A can walk to D. Now we can't head backwards because we've already used that edge once. From D, we can move to B. We can't move backwards because, again, we've used that edge. And then B can move to C. So you'll notice in this sequence of adjacent nodes, we use each node and each edge exactly once. We will be focusing on paths today. Now, there's a difference between paths and what we'll call shortest paths. Suppose you pick any pair of nodes in your network. Here is a path from our first node to our second node. Now we can walk along this edge, and along this edge. So this would have us traverse 3 different edges to get from our first node to our second. This is a path, but it's not a shortest path because we could have gotten from our first node to our second node in a far quicker manner using only one edge by just going there directly. So the difference between just a regular path and a shortest path is a shortest path will use the fewest number of edges possible. So in this particular case, for this particular pair of nodes, there's only one shortest path, and its length is equal to 1. Its length is simply the number of edges that we use in that path. Now it's important to note that if you fix a pair of nodes, the shortest paths in between those two nodes are not necessarily unique. So for example, to move from our first node to our second node in this case, we could follow this particular shortest path. It has a shortest path length of 2. However, there's an alternate path that we could take that also qualifies as a shortest path because we get there in exactly 2 edges. So in this case, for this pair of nodes, there are 2 shortest paths. Each are of length equal to 2. Now, when we talk about computing diameter, remember the idea is for a fixed network, we're going to randomly choose a pair of nodes, and we want to know how long does it take to get from one node to the other via a shortest path. So the shortest path length is what we're going to be looking at here. But since our nodes are randomly determined, we're going to have to look at all possible pairs of nodes, compute the lengths of the shortest paths for each one of those possible pairs, and then if we pick the largest one, that's going to be our worst case scenario. So here's how we can do this. Let's break this into steps. It's going to be a little bit easier to visualize this if I label my nodes with letters rather than people. We're going to consider all possible pairs of nodes, and then we're going to find the length of the shortest paths in between those pairs. So the first thing that we need to do is figure out what are the possible pairs of nodes. Start by considering all the pairs that are paired up with A. In this case, we're going to ignore the edges. So just take those out of your mind. Fix A in your mind, and now think about what are the other nodes that we could pair off with A? Well, there's A and B, so we'll write that down. There's A and C, there's A and D, and there's A and E. So these are all the pairs that will involve A. So let's ignore A now. We've already considered all the pairs with A. And now let's jump to our next node, which is B. B could be paired with C, B could be paired with D, and B could be paired with E. Now in our next iteration, we would ignore B and consider the last 3 nodes that we haven't worked through yet. And then we would keep continuing this process until eventually we run out of pairs. If you want to pause the video at this point and figure out what are the remaining pairs of nodes that we haven't considered yet, please do. You can check your answer right after that. Okay, so hopefully you have these answers. If you'll notice, this first column looks at all of the pairs that start with A. Our second column looks at all of the new pairs that could start with B. Our third column looks at all the new pairs that could start with C. And our final column is all the remaining pairs that start with D. Now, if we consider the pairing A and C, we don't have to consider C and A separately. So in some sense, looking at the list here removes a certain bit of redundancy in that a pairing A and C should be considered the same as a pairing C and A. So these are all of the possible pairs that we need to consider when we're looking at random starting and stopping points inside of our graph. Our next step is to take all of those pairs for consideration and then compute the length of the shortest path in between those two nodes. So if we start with AB, we have a shortest path length of 1. So we can put the length of 1 inside the table to its right. Looking at AC, again, we see that these are directly connected by an edge, so it has a shortest path length of 1 as well. Now, A and D is a little bit trickier. For A and D, there are a number of ways we could get there. We could move from A to C to E to D. This would take a path length of 3, but this is not the shortest path in between A and D. Instead, moving directly from A to E and then E to D would get us there in 2 steps. This is in fact one of the shortest paths. Its length is 2. The other one would go from A to B and then to D. So the shortest path length between these 2 pairs is 2. We know it's not 1. Of course, there's no direct connection between A and D. At this point, if you want to pause the video and fill out the rest of this table, considering A and E, B and C, etc., etc., fill in the shortest path lengths and then check your answers. So hopefully you got these answers. We now have a table where we consider all unique pairs of nodes that could serve as our starting stop points, and then the length of the shortest path in between them. Now remember, we wanted to answer the question, worst case scenario, what's the longest I'll have to walk if I'm randomly starting at a point and walking to a random stopping point? Right? The largest number in this table of values is going to be the longest possible path that you would have to walk from any starting point to any stopping point. This is what we call our diameter. So we look down this list, we find the largest value, which would be the longest of the shortest paths between a pair of nodes, and that ends up being our diameter. Let's consider some examples. A complete network is one in which every node shares an edge with every other node in the network. In other words, if you pick any pair, there's a direct edge that connects one to the other. Now in this case, we don't have to make a table of values. Since every node can travel to any other node using exactly one edge, we know that that table is just going to be a bunch of 1s. In this case, for a complete network, the diameter is always 1. Here's an example of a bucket brigade. So suppose we have a lake over here, and then a fire over here by node 12. The idea of the bucket brigade is person 1 passes a bucket of water to person 2, who passes to bucket 3, and that water travels along this chain, quickly and easily getting the bucket of water to the person who's trying to put out the fire. Now, if you're looking at the diameter of the bucket brigade, remember, we're looking for the worst case scenario. What's the longest distance that a bucket would have to travel? To do that, you want to focus on the 2 nodes which are quote-unquote farthest apart in this chain. So that would be the first node and the 12th node. And if you think about how many edges separate these two nodes, you can count to see that our diameter in this case is 11. Now, suppose you had a bucket brigade with some unspecified number of people into it. Then the longest that bucket of water would ever have to travel would always start at whoever filled the bucket and stop at whoever's pouring it on the fire. Now, in this case, to move from 1 to 2, we use an edge. From 2 to 3, we've now used 2 edges, etc., etc., etc. Convince yourself that in general, for a bucket brigade or for a nice chain of length n, your diameter in this case is always going to equal the total number of nodes minus 1. Now, when we start dealing with some real-world data, some actual networks, other graphs, the diameter's much harder to compute. And so this is the reason why we often employ computational methods. Let me give you a sense of why it's best to use a computer to compute the diameter for more complicated graphs. First of all, recall our steps for finding this diameter. First, we listed out all possible pairs of nodes, and then for each pair of nodes, we found the length of the shortest path in between them. From that list of shortest path lengths, we chose the largest value, and that ended up being our diameter. The first step is one that can be very time-consuming to do. List out all possible pairs of nodes. Here's a quick little table that gives you a sense of how much work would be involved in this. The network that we considered had 5 nodes in it, and it ended up having us check about 10 different pairs of nodes. If we had a network with 10 nodes, we would end up checking 45 pairs. 15 nodes increases us to 105 pairs. 25 nodes has us doing 300 pairs. And if we have a network with 100 nodes in it, which isn't too unlikely, we might have to check 4,950 pairs of nodes in order to get this done. This is not something that we want to do by hand. This is definitely something we want to employ a computer for. So when you're interpreting the diameter of a network, I think it's really helpful to keep our game in mind. Suppose we're playing the game where we want to walk from a randomly chosen start node to a randomly chosen stop node. We can ask ourselves, worst case scenario playing this game, what's the longest distance I'll ever have to walk? This is exactly what the diameter measures. If it helps, you can remember this by playing the exact same game inside of a circle. Pick any 2 points inside of your circle. The shortest path between them always ends up being a straight line, and we can think of the length of that shortest path as being the length of the line. So if we pose the question where we're playing inside of our circle, given 2 random points in the circle, we'll walk along the shortest path or a straight line in between them, that's the length of our shortest path. So given that we're randomly selecting these points, what is the longest we'll ever have to walk from one point down a circle to another point on a circle? This ends up exactly being the diameter that we're familiar with from mathematics classes in geometry. So this is our idea for the diameter of a network.